Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series. Today we are exploring quantum computing hardware and the battle against decoherence.
It is genuinely wonderful to be here.
Yeah.
And the collection of papers, preprints, engineering reports we are exploring today, it spans from late 2024 right through early 2026.
It's a massive stack.
It really is. And what this information chronicles is, honestly, without exaggeration, arguably the most complex engineering challenge humanity has ever undertaken.
Ever.
Yeah, ever. We are collectively trying to build machines of unimaginable, almost godlike computational power.
Right.
But the central conflict running through all of this research is that the universe itself.
Yeah. Reality, basically.
Exactly. The natural background noise of reality is fighting us every single step of the way.
And that dynamic, that fight, is exactly the mission of today's exploration. We're looking at a literal battle between human engineering and the fundamental laws of thermodynamics and quantum mechanics.
Absolutely.
So for you listening, we are going to navigate this massive landscape by, well, starting with the foundations.
We have to.
Right. We really need to unpack how these incredibly delicate machines actually work and what physicists currently think they know about the environment they operate in.
Which is always changing, by the way.
Oh, constantly. From there, we will wade into the active debates because there are fierce disagreements happening right now in the scientific community.
Material choices, shielding methods.
Exactly. How to deal with microscopic saboteurs that are just ruining calculations.
It gets wild.
It does. And after that, we're going to look at the frontiers. You know, the mind-blowing breakthroughs like Google's Willow chip, things that are currently shattering theoretical ceilings.
Yeah.
And finally, we will wrap up with the massive implications this technology holds for our global society, our economy, and even our philosophical understanding of the universe.
It is a journey that really, it forces you to change how you look at the physical world. To truly appreciate the massive breakthroughs of 2025 and 2026, we first need to make sure we're completely grounded in the physics of what a quantum computer actually is.
Right. Let's set that baseline.
So if you look at the classical device you're using to listen to this right now.
Like your smartphone or a laptop.
Yeah, it operates on classical bits. At the absolute foundational hardware level, everything boils down to a physical state of either a 0 or a 1.
High voltage or low voltage.
Exactly. It's binary, it's definitive, and crucially, it is sequential.
Right, sequential is the key word there. A classical computer, even a massively powerful supercomputer, essentially tries possibilities one by one.
Yeah.
I always like to picture it as a person walking through a massive, sprawling physical maze. You know, you walk down one path, you hit a dead end, you physically turn
You
around.
go all the way back.
Exactly. Walk back and try the next path. Now, you do this incredibly fast, millions of times a second, but you are still doing it sequentially.
It's one at a time.
Right. But a quantum computer uses qubits, which completely throw those classical rules out the window.
They really do.
And the literature highlights three core concepts we need to thoroughly unpack to understand how qubit functions: superposition, entanglement, and interference. Let's start with superposition.
Okay.
And let's use an analogy to help visualize what's happening. Imagine you have a highly complex, massive equation to solve, and you are writing it out on a giant whiteboard.
A classical computer is like a single mathematician standing at that whiteboard, trying out one potential solution, realizing it's wrong, erasing it, and writing out the next attempt.
Right.
But a quantum computer leveraging superposition is fundamentally different. It is not trying one solution at a time. Superposition allows the qubit to exist in a complex linear combination of both 0 and 1 simultaneously.
Both at once.
Yes. So in our whiteboard analogy, it is like you have managed to write every single possible solution on that whiteboard at the exact same time.
Wow.
You are keeping a vast multitude of possibilities alive and active within the machine all at once.
It's like keeping all the doors in the maze open simultaneously.
That's a great way to look at it.
But, you know, keeping all the possibilities alive isn't enough to actually compute anything complex. Which brings us to the second concept.
Entanglement?
Right. If we stick to our whiteboard analogy, entanglement means that certain variables in those simultaneous equations are inherently physically linked to one another.
Precisely. Entanglement is what Einstein famously called spooky action at a distance.
Spooky action.
Yeah, in a quantum processor, if you entangle two qubits, their physical states become mathematically inseparable.
Okay, meaning what, practically?
Meaning, if a variable changes in one part of your incredibly complex equation on the whiteboard, its entangled partner instantly and predictably adjusts in another part of the board.
Regardless of the physical distance between them on the chip.
Exactly. They no longer operate as independent bits. They move and evolve together as a single, unified quantum system. This is what allows a quantum computer to process vast amounts of interconnected data.
Okay, so we have all the possible answers written on the board at once, and the variables are all linked together so they update as a unified system.
Right.
But here's the question that always trips people up. If the machine is holding millions of possible answers simultaneously, how do you actually get the one correct answer out of it?
The measurement problem.
Yeah, because if you just look at it randomly, wouldn't you just get a random result?
You would.
So this is where the third concept, interference, comes in. And I feel like this is the actual magic trick of quantum computing.
It is the absolute core of quantum algorithmic design. Interference relies on the wave-like nature of quantum probabilities.
Okay.
Think of tossing two pebbles into a calm pond.
Sure, ripples.
Right. The ripples spread out and interact. Where the crest of one wave meets the crest of another, they amplify each other. That is constructive interference.
Okay, bigger.
Yes. But where a crest meets a trough, they cancel each other out. That's destructive interference. A quantum computer is programmed using specialized algorithms to choreograph this exact phenomenon.
So the algorithm acts like a maestro, conducting the probabilities.
Very much so.
It uses cancellation and reinforcement. It makes the wrong answers destructively interfere with each other so their probabilities literally fade away to near zero.
Yeah.
While the right answers constructively interfere, amplifying their probabilities until they stand out brightly on our metaphorical whiteboard.
That is exactly how it works. You run the quantum algorithm, the wave functions interfere, and when you finally make a measurement, the system collapses with an overwhelmingly high probability into the correct classical answer.
It's brilliant.
It is. But
there's always a but.
There is a massive catch, and it forms the core of our entire discussion today. To perform this beautiful choreography, the whiteboard must be perfectly, flawlessly isolated from the rest of the universe.
This is the central conflict.
Yes. If even a single particle of ambient heat, a stray magnetic field from a power line down the street,
or a cosmic ray,
or a cosmic ray from a distant supernova, if any of that interacts with our delicate quantum whiteboard, the universe essentially looks at the system.
And in quantum mechanics, observation destroys the superposition.
The wave function collapses. The whiteboard starts rapidly, violently erasing itself every tiny fraction of a second, simply because the environment brushed up against it.
Wow.
This is the battle against nature we are talking about.
And to fight this battle, humanity isn't just trying one single method. The engineering consensus right now is, honestly, beautifully chaotic.
They're chaotic.
The landscape of the industry looks like what I'd call a modality menagerie. 5 prominent, completely different physical architectural approaches to building a qubit.
It really is a menagerie.
It's like having 5 different architectural firms tasked with building a skyscraper that reaches the moon, and they are all using completely different materials.
Right.
Let's walk the listener through these 5 approaches, starting with the most famous right now, superconducting quantum computers.
Superconducting qubits are indeed currently leading the commercial race. This is the architecture championed by major players like IBM, Google, and IQM.
Okay, how do they work?
Well, they don't use single atoms. They use microscopic scale electrical circuits printed on silicon or sapphire chips.
Well, like regular computer chips.
Similar fabrication, yes. But to make them behave quantum mechanically, you have to cool these circuits down to near absolute zero.
And when we say near absolute zero, we are talking colder than the vacuum of deep space. We are talking millikelvins.
Exactly. They use massive, incredibly intricate dilution refrigerators. If you've ever seen a picture of a quantum computer, you are usually looking at this cooling system.
Right. They look like giant golden steampunk chandeliers.
Perfect description. At the very bottom of that chandelier, the temperature is so cold that the specific metals used in the circuit lose absolutely all electrical resistance.
They become superconductors.
They become superconductors. The quantum information is then stored in the oscillating microwave currents flowing endlessly back and forth within these frictionless circuits. And you manipulate them with incredibly precise microwave pulses.
So it's essentially manipulating synthetic atoms using microwaves in a deep freeze.
Yes.
But then you have the second approach, which feels almost elegant in contrast, photonic quantum computers.
Right.
Companies like Xanadu or CA Computing, PsiQuantum are heavily invested here. Instead of freezing electrical circuits, they use actual individual particles of light, photons.
The primary advantage of photonic qubits is that photons barely interact with their environment. They don't have mass or charge.
So they just pass through things.
Pretty much. This means they are relatively lossless over long distances, which makes them absolutely fantastic for quantum communication.
Like the future of a quantum internet.
Exactly. And crucially, you don't necessarily need to freeze the entire system to absolute zero just to get the photons to travel from point A to point B.
But wait, if they don't interact with their environment, how do you get them to interact with each other to perform logic gates and entanglement? That sounds like a massive engineering headache.
It is a profound challenge. Trapping, delaying, and forcing photons to entangle requires incredibly complex optical mazes.
Beam splitters, mirrors.
Specialized crystals. It is very hard to keep a photon sitting still.
I can imagine. Which brings us to the third modality, one that has been a massive surprise in the industry recently, neutral atom quantum computers.
Yes, the dark horse.
This is where the science fiction element really kicks in for me. Companies like Quera, Pascal, Atom Computing are leading this. Tell us how they are building qubits out of neutral atoms.
Instead of manufactured circuits or racing photons, they use nature's own perfect qubits. Identical uncharged atoms, typically elements like rubidium or cesium.
Uncharged, so neutral.
Right. They take a cloud of these atoms and suspend them inside a complete ultra-high vacuum chamber. Then they use ultra-focused, perfectly tuned laser beams to grab individual atoms.
Just grab them.
Yes. These laser beams are literally referred to in the physics community as optical tweezers.
Optical tweezers, using light to physically grab and hold a single atom in empty space.
Yes. The lasers exert a physical force that suppresses the atom's movement, which effectively cools them to near absolute zero.
While holding them
In a perfectly spaced two-dimensional or three-dimensional grid. The quantum information is stored in the electron energy levels of these trapped atoms, and you perform calculations by pulsing other lasers at them.
That is fundamentally different from our fourth type, which sounds similar but has a totally different control mechanism, trapped ion quantum computers.
Right, championed by companies like Quantinuum and IonQ.
Instead of uncharged neutral atoms held by lasers, this method uses charged atoms, ions.
The electrical charge changes the engineering completely. Because ions have a net positive or negative charge, they interact strongly with electromagnetic fields. So, researchers design specialized chips that project a precise, oscillating electromagnetic field above their surface. The ions get trapped in this invisible electromagnetic bowl,
Hovering in a vacuum.
Because they repel each other due to their identical charges, they naturally space themselves out in a perfect crystalline line or grid.
Like magnets pushing away from each other.
Exactly. We then use lasers or microwaves to manipulate their natural quantum states.
And finally, we have the fifth major approach in the menagerie, quantum dot computers, heavily pushed by companies like Dirac and Silicon Quantum Computing. This one feels like it bridges the gap between our current laptops and the quantum future.
It really does. Quantum dots are essentially nanoscale semiconductor particles. They're often referred to as artificial atoms.
Okay, how so?
By carefully engineering a semiconductor matrix, usually silicon, researchers can trap a single solitary electron in a tiny physical well.
Just one electron.
Just one. Once trapped, they use incredibly precise magnetic or electric fields to manipulate the spin of that individual electron. You can think of spin as a microscopic compass needle.
Up or down.
Right. Spin pointing up might represent your 0, and spin pointing down represents your 1.
The massive advantage here is the manufacturing, right?
Yeah.
We already have massive multi-billion-dollar fabrication plants scattered across the globe that excel at printing nanoscale features on silicon.
That is the immense economic promise of silicon spin qubits. If quantum dots are the winner, we can theoretically piggyback on the existing classical semiconductor industry to achieve mass production.
Wow. But, regardless of which of these 5 paths you take,
Superconducting circuits, racing photons.
laser-trapped neutral atoms, electromagnetically trapped ions, or electron spins in silicon,
Right.
you inevitably slam into the ultimate nemesis of this entire endeavor, quantum noise and decoherence.
Still here.
This is the universal villain of our story today. But let's really define what this is physically. When we say decoherence, we're talking about the physical process where a quantum system loses its coherence, its ability to maintain that delicate superposition and entanglement we talked about.
In the strict language of physics, decoherence occurs when a quantum system leaks which path information to the surrounding environment.
Which path information?
Think back to the classic double-slit experiment from high school physics, where a particle can pass through two slits simultaneously as a wave, creating an interference pattern.
Right.
If the environment interacts with that particle in a way that reveals which slit it actually went through.
Even if no human is looking.
Exactly. Even if no human is looking, the wave nature collapses. The pure quantum state degrades into a classical statistical mixture. The magic is gone. The whiteboard is erased.
And looking at the research, they break this decay down into two primary channels. I think understanding these two channels is really helpful for grasping exactly how the quantum state falls apart. The first channel is called amplitude damping.
Amplitude damping is essentially the loss of energy, also known in the literature as relaxation.
Okay.
Imagine your qubit is excited into the one state. It is holding on to a tiny packet of extra energy. Amplitude damping happens when the qubit physically loses that energy to its environment.
How does it lose it?
Perhaps by emitting a stray photon or creating a tiny vibration in the chip. When it loses that energy, it falls from the excited one state back down to the resting ground zero state.
Just runs out of gas and drops.
Pretty much.
That makes intuitive sense. But the second channel, phase damping, is much more insidious. It's also called pure dephasing. And the reason it's so frustrating is that it happens without any loss of energy at all.
Exactly. The qubit doesn't fall from 1 to 0. Instead, the relative phase between the 0 and 1 states in the superposition is randomized.
Randomized how?
Well, if we think of superposition as a perfectly synchronized pendulum swinging back and forth with a highly specific rhythm, phase damping is like a microscopic, chaotic vibration in the room. The pendulum doesn't lose its momentum. It is still swinging with the same energy, but it loses its perfectly synchronized rhythm. It gets knocked out of step.
And in a quantum computer, what causes that?
It is frequently caused by fluctuating background magnetic fields or even tiny imperceptible instabilities in the lasers controlling the qubits.
So to fight this dual threat of energy loss and rhythm loss, you have to be able to map it. You can't defeat an enemy you can't understand.
You really can't.
And the mathematical frameworks physicists use to model this noise are intensely, punishingly complex. They use what are broadly called quantum master equations. Let's spend some time unpacking the main ones mentioned in the sources because it shows how our understanding of reality is evolving. Let's start with the foundational one, the Lindblad equation.
The Lindblad equation is the bedrock of modeling quantum noise. It represents a Markovian model of the environment.
Markovian?
To understand Markovianity, you have to think about the concept of memory. A Markovian environment has absolutely no memory.
None at all.
The assumption here is that once a piece of quantum information leaks out of the qubit and dissipates into the environment, it is instantly gone forever. It will never return to influence the qubit again.
I really love the analogy physicists use for this. It's like a leaky bucket. The qubit is the bucket. The quantum information is the water. In a Markovian model, any water dripping out of the bucket instantly vanishes from existence.
It's a completely one-way street of information loss.
Right. And mathematically, the Lindblad equation is fantastic because it's safe. It always generates valid physical quantum states, what physicists call completely positive and trace-preserving states. It never outputs a mathematical impossibility.
True.
But what if reality doesn't actually work like that? What if the environment does remember?
That is exactly the limitation of the Lindblad equation and where the Redfield equation comes in.
Okay.
The Redfield equation is a non-Markovian model. It is a second-order perturbative approach that actually retains the correlation between the system and the environment.
So it remembers.
It mathematically accounts for the fact that sometimes, especially in systems where the qubit is strongly coupled to its surroundings, a bit of information might leak into the environment, slosh around in the surrounding atoms or electromagnetic fields, and actually push back on the qubit at a later time.
The environment remembers the leak.
It remembers the leak.
So it's like the leaky bucket is sitting inside a slightly larger tub. The water leaks out, but it pools around the bucket, and eventually some of that water might splash back in.
Exactly.
But I'm reading the literature here, and it notes a massive, glaring problem with the Redfield equation. Because it tracks that back and forth memory. If the coupling to the environment is too strong, the math breaks down and leads to profoundly unphysical results.
It does. It can actually predict negative probability.
Negative probabilities.
Yeah.
Which obviously do not exist in the physical universe. You cannot have a negative 30% chance of an atom being in a certain state.
Precisely. And that deep mathematical tension between the safe but overly simplistic Lindblad equation and the more realistic but mathematically dangerous Redfield equation. That leads us to a major theoretical breakthrough from the 2024 to 2026 timeframe discussed in our materials.
Oh, yeah.
Researchers developed what is called the universal Lindblad-like, or ULL, equation.
I really want to dig into this. How did they solve the tension?
They found a way to resolve the discrepancies by imposing what they call energy conservation on the Born level.
Let's translate that.
The Born level refers to the very first immediate primary layer of interaction between the quantum system and the bath of noise surrounding it.
The initial splash.
Yes. By mathematically strictly enforcing that energy must be conserved at this very first layer of interaction, they created an equation that does something remarkable. It accurately predicts short-time non-Markovian memory effects, the sloshing back and forth of information,
while strictly maintaining physical positive probabilities.
It doesn't break the laws of math.
That is incredible. It gives physicists a highly accurate, reliable map of exactly how qubits interact with their messy, noisy environments in those crucial first fractions of a microsecond.
Which is exactly what we need to build better hardware.
It's amazing how the foundational math had to evolve just to allow us to properly observe the enemy we are fighting. Which brings us perfectly to the second phase of our exploration today, the active debate.
This is where it gets highly practical and very contentious.
Yes, this is where the pristine theories of the blackboard hit the incredibly harsh, frustrating reality of the laboratory. And nowhere is this more dramatic than the material wars currently raging in the world of superconducting qubits.
The material wars are a fascinating study in how a single atomic layer of material can literally make or break a billion-dollar quantum processor.
A single layer.
For years, niobium was the absolute standard metal used to build superconducting qubits. It has a high critical temperature, meaning it becomes superconducting relatively easily, and it is highly compatible with existing industrial-scale manufacturing techniques.
It was the workhorse of the industry. But niobium has a fatal flaw. Its surface oxidizes when exposed to air, and that microscopic oxide layer hosts a swarm of tiny, chaotic defects that cause intense decoherence.
It was severely limiting how long the qubits could hold their state.
So then, we see this massive breakthrough at Princeton University, led by Nathalie de Leon. They decided to look at the periodic table, ditch the niobium in the qubit's capacitor, and replace it with tantalum.
And the results were stunning. The Princeton team showed that tantalum yielded record-breaking coherence times because it radically reduced the dielectric loss at the metal-air interface.
The surface was cleaner.
Tantalum's native oxide is much more stable and less noisy than niobium's. Almost overnight, tantalum became the new golden child of the quantum industry. Everyone thought niobium was old news, a relic of the early days.
But science is rarely a straight line. Fast forward to a preprint paper from ETH Zurich in February 2026 by Michael Kirschbaum and his team. They dropped a massive plot twist on the industry.
A huge twist.
They discovered that while tantalum is indeed fantastic at preventing that surface oxide loss, it is incredibly, uniquely sensitive to a completely different type of noise called quasi-particle-induced decoherence. And the source of this noise, ambient infrared radiation.
Infrared radiation. Literally just the ambient heat radiation floating around in the laboratory environment or radiating from the slightly warmer upper stages of the cryogenic fridge.
Just the heat glow.
The 2026 data clearly showed that tantalum acts like an antenna for this specific infrared noise. The photons of infrared light hit the tantalum, break the superconducting Cooper pairs of electrons, and flood the qubit with rogue quasiparticles that completely ruin the computation.
And here's the absolute kicker. Niobium, the old, discarded workhorse material, turns out to be practically immune to this specific infrared noise.
Its energy gap is different, so the infrared light just doesn't affect it the same way.
It is a textbook example of the maddening complexities of quantum engineering. You solve one massive problem by changing materials, and you inadvertently expose a glaring vulnerability to a completely different environmental factor.
It's like plugging one hole in a boat and two more spring open.
Exactly. So the mitigation strategy the Zurich team proposed wasn't to throw out tantalum, but to add heavily engineered inline infrared filters to the wiring and install ambient infrared absorbers inside the cryostat.
Which worked. When they installed those filters, blocking the heat glow, the quasi-particle tunneling rates dropped dramatically, down to 100 Hz for niobium and 300 Hz for tantalum.
It proves that as we push for longer and longer coherence times, we have to look at entirely new, subtle radiative backgrounds that we previously ignored as insignificant.
And it's not just the ambient glow of infrared radiation causing headaches. We have to talk about the microscopic saboteurs. When we tell you these machines are sensitive, it is genuinely hard to overstate just how sensitive they are. The enemy isn't just someone bumping the table, the enemy is subatomic. One of the main culprits highlighted extensively in the engineering reports are TLS, or two-level systems.
Let's define a two-level system for the listener. Because a qubit is technically a two-level system, right? Yeah. So why is a TLS a saboteur?
A qubit is a perfectly engineered, highly controlled two-level system. The TLS defects we are talking about are unwanted, microscopic imperfections naturally occurring within the amorphous dielectric materials and the interfaces of the circuit.
So they are flaws.
Think of them as rogue, tiny, wild quantum systems living inside the chip's substrate. They are basically atoms or groups of atoms that can toggle back and forth between two positions.
Now, they act like tiny, chaotic sponges. They fluctuate, causing localized charge noise and high-frequency dielectric loss. They essentially absorb the delicate microwave energy right out of the qubit, hold it for a moment, and then spit it back out randomly at the wrong time,
completely ruining the precise wave choreography we talked about earlier.
They are microscopic parasites.
Precisely.
But if the microscopic defects naturally living inside the chip weren't bad enough, the active debate also focuses on enemies coming from outer space.
Right. High-energy impacts from cosmic rays and ambient ionizing radiation.
This sounds like a sci-fi movie pitch, but it's a massive daily problem for these labs. A high-energy particle, a cosmic ray from across the galaxy, can travel through the Earth's atmosphere, pass right through the laboratory roof, pass through the metal casing of the dilution refrigerator, and strike the silicon substrate of the quantum chip.
And when it strikes, it acts like a microscopic bomb. It deposits a massive plume of energy into the crystal lattice. This energy shatters the superconducting pairs of electrons across a wide area, creating a massive wave of errors across multiple qubits simultaneously.
In classical computing, a cosmic ray might flip a single bit once in a blue moon.
But in a tightly packed quantum processor, a single strike can poison a dozen qubits at once, making error correction nearly impossible.
The solutions being debated for this are extreme. We are looking at proposals to move commercial quantum computers into shallow underground facilities. They calculate you need the equivalent of 30 meters of solid water shielding just to effectively hide the chips from the secondary spray of cosmic rays.
Or, if you can't go underground, researchers are constructing massive cryostats shielded with tons of heavy ancient lead to block out both cosmic rays and the naturally occurring gamma rays emitting from the concrete in the laboratory walls.
Concrete has gamma rays.
Small amounts, yes, enough to ruin a qubit. A comprehensive 2024 paper predicted that deploying this kind of heavy shielding could reduce correlated multi-qubit errors by a massive factor of 20.
Building lead-lined bunkers deep underground just to do math. It really shows the stakes of what we're dealing with.
It does.
But I have to admit, out of all the incredibly dense high-level physics in these sources, the thing that actually made me react the most, I actually laughed out loud, was the glue problem.
Ah, yes, the glue.
Because we're talking about billion-dollar ultra-advanced cryogenic hardware, shielded by lead, cooled to near absolute zero, and they're being sabotaged by the glue.
It is a very humbling, frustrating reality check for the physicists. You can perfectly engineer a pure quantum state, but if the standard industrial adhesive holding your perfectly engineered chip to the copper mount fails, the whole thing is worthless.
Let's explain why the glue fails, because it's not that the chip just falls off. A 2024 study showed that the simple act of gluing a silicon crystal to its mount generates tiny microscopic thermal stresses.
Because as the glue and the silicon crystal cool down from room temperature to absolute zero, they contract at slightly different rates.
They have different coefficients of thermal expansion.
Exactly. So massive tension builds up at the interface, and eventually that stress periodically snaps and relaxes. When it snaps, it creates tiny microscopic microquakes in the chip, releasing what are called phonon bursts.
Phonons, let's translate that. A photon is a particle of light. What is a phonon?
A phonon is essentially a quantized packet of sound or vibrational heat wave traveling through the physical crystal lattice of the chip.
Okay.
The mechanical stress from the glue snapping creates these phonon bursts. When a high-energy phonon wave crashes into the superconducting circuit on the surface, the physical vibration contains enough energy to literally break the Cooper pairs of electrons that carry the frictionless superconducting current. It poisons the qubit with unwanted heat and quasi-particles.
The glue creates a microscopic earthquake that shatters the quantum state.
Right.
It perfectly illustrates that in quantum hardware development, classical mechanical engineering, like exactly how you glue two physical parts together without creating tension, is just as critical as the theoretical quantum physics.
Everything matters at that scale.
So with all these saboteurs, infrared radiation from the walls, cosmic rays from space, microscopic TLS parasites, and literally the glue holding the machine together, how do we fight back? How do we keep the whiteboard clean?
Well, the active debate outlines three main pillars of error management.
Let's walk the listener through them. The first pillar is error suppression, specifically a technique called dynamical decoupling, or DD.
Dynamical decoupling is a highly active, incredibly fast-paced defense mechanism. It doesn't try to shield the qubit from the noise. It tries to actively outmaneuver it.
How?
It involves firing a highly calculated sequence of very fast, strong electromagnetic microwave pulses directly at the qubit while it is idling.
I think the car alignment analogy works perfectly here. Imagine you are driving a car on a long highway, and the car has a severe alignment issue. The steering constantly pulls hard to the left due to a crosswind or a mechanical flaw. That crosswind is the low-frequency background noise slowly pushing the qubit's delicate phase out of alignment.
Right. If you know the car keeps pulling to the left, you can't just let go of the wheel. Dynamical decoupling is the equivalent of the driver intentionally, sharply yanking the steering wheel to the right every single second.
Just constantly correcting.
You fire a pulse that mathematically flips the qubit's state. So the continuous noise that was pushing it away from its target is now, after the flip, pushing it back toward its original correct position. You are essentially averaging out the slow, drifting noise over time by constantly, aggressively flipping the qubit's orientation.
It's exhausting just to think about, but it works brilliantly for slow-moving noise. But what about fast, chaotic noise? That brings us to the second pillar, error avoidance, which utilizes something called decoherence-free subspaces, or DFS. This is such a profoundly cool conceptual approach.
It truly is elegant. Instead of actively fighting the noise like DD does, error avoidance looks for deep underlying symmetries in how the environmental noise interacts with the quantum system.
Symmetries.
Right. Instead of storing your piece of information in a single vulnerable physical qubit, you encode your quantum information into a specific mathematically defined collective state spread across multiple physical qubits. You create a quiet zone.
So it's like finding the eye of the hurricane. You just position the data in the center and let the noise rage around you.
That's a great way to visualize it. If a fluctuating ambient magnetic field washes over the chip, hitting all the physical qubits equally and symmetrically, the relative encoded information that lives between them remains entirely unaffected.
The environmental noise naturally and perfectly cancels itself out within that specific subspace.
The qubits might be spinning chaotically, but their relationship to each other, which holds the data, remains pristine.
It's brilliant. And the third pillar is error mitigation and correction, which essentially leans on software and classical post-processing supercomputers to analyze the slightly flawed outputs of the quantum machine and mathematically deduce and subtract the noise biases.
But what is truly thrilling in the recent literature is that an experimental milestone on IBM quantum processors actually managed to combine the first two pillars.
Yes, this was a major step forward. Researchers managed to combine the active pulsing of dynamical decoupling with the passive protection of decoherence-free subspaces for the very first time.
They essentially used the incredibly fast, sharp pulses of DD to artificially induce the symmetries needed to create a DFS in a system where those symmetries didn't naturally exist.
So they aggressively steered the car directly into the eye of the hurricane.
Precisely. By orchestrating this, they created logical qubits that demonstrated up to a 23% measured improvement in preserving the pure quantum state compared to using just physical qubits with DD alone. It proved that these defensive pillars are not mutually exclusive. They can be layered.
Which brings up what is arguably the most massive active debate and economic divide in the field right now.
The scaling debate.
Right. Can we reach utility scale computing?
Mm.
meaning the quantum computer is actually economically useful for solving real-world, highly complex problems,
Mm.
using just these pre-fault tolerant mitigation and suppression methods? Or do we have to wait a decade or more until we have pure, flawless, fully error-corrected logical machines?
That debate is the absolute crux of the current commercial race. Do we squeeze every single ounce of utility out of these noisy intermediate-scale quantum or NIQ devices using incredibly clever software mitigation? Or is that a dead end, and we must hold out for the holy grail of perfectly error-corrected topological qubits?
The sources point to a landmark IBM the 127 qubit experiment from 2023 that heavily argues we can achieve massive utility before pure fault tolerance. They used advanced error mitigation techniques to accurately measure highly complex quantum states that the absolute leading classical approximation methods on supercomputers simply couldn't handle.
They prove the noisy machines can do useful physics right now.
It is an ongoing fierce debate between the hardware purists and the software mitigation optimists. And this tension, this desperate push to scale up despite the noise, transitions us perfectly to the third major part of our exploration today: the frontiers.
The frontier.
These are the breakthroughs, the sudden leaps in logic and engineering from late 2024 through 2026 that might change everything we just talked about. And standing at the absolute forefront of these frontiers is the undisputed dark horse of quantum computing: the rise of neutral atoms.
If you asked the leading experts 5 or 6 years ago, superconducting qubits were the undisputed kings of the hill. They had the funding, they had the momentum, but by the end of 2024 and through 2025, neutral atom platforms had completely shocked the industry.
That came out of nowhere.
They scaled faster and better than anyone predicted.
Let's explain why they suddenly leaped forward. Because holding atoms with lasers sounds impossibly hard to scale. But it all comes down to leveraging a specific fascinating physical phenomenon called the Rydberg blockade.
The Rydberg blockade is an incredibly elegant natural phenomenon in atomic physics. In a neutral atom processor, you have that 2D or 3D grid of uncharged atoms gently held in a vacuum by optical tweezers. To perform a calculation, you need to entangle 2 atoms. To do this, you fire a highly specific laser pulse to excite the first atom into what is called a Rydberg state.
Let's define a Rydberg state because it sounds like a superpower for an atom.
It essentially is. When an atom absorbs the laser energy and enters a Rydberg state, its outermost electron is pushed incredibly far away from the nucleus. The atom physically swells to a massive size, on an atomic scale, of course.
Sure.
This massive separation of positive and negative charge creates a gigantic electric dipole moment. The atom is suddenly projecting a massive electric field around itself.
And here is the VIP bouncer analogy.
Yeah.
Imagine that first atom gets hit by the laser and swells up to massive VIP status. Its newly formed massive electric field acts exactly like an aggressive bouncer at the door of an exclusive club.
Right.
It physically, electromagnetically blocks any neighboring atom within a 5 to 10 micrometer radius from being excited into that same Rydberg state, no matter how hard you hit that second atom with a laser. You can only have one VIP in that specific radius at any given time.
That exclusion principle, the fundamental physical fact that the state of the second atom is entirely conditionally dependent on whether the first atom was excited, is exactly the mechanism you need to create a flawless conditional logic gate, like a controlled Z gate.
Just by shining light.
It allows for brilliant, high-fidelity, on-demand 2-qubit entanglement just by flashing a laser at a pair of atoms.
And the advantages of building a computer this way are staggering. The first massive advantage is 2D and 3D scalability. Think about the superconducting qubits we discussed earlier. They are physical, macroscopic metal circuits physically wired together on a 2D silicon chip. To add more qubits, you need more wires, more microwave lines, more physical space.
It gets incredibly crowded and introduces severe crosstalk noise.
But neutral atoms are completely different. They are just individual atoms floating in an empty vacuum held by light. There are no wires. To add 1,000 more qubits, you just shine a wider pattern of optical tweezers into the chamber and load more atoms.
In 2024, a massive breakthrough by a team led by Quera researchers demonstrated an array of up to 6,139 atoms.
6,000. When superconducting chips are fighting for a few hundred, that is, thousands of pristine qubits dynamically held in a programmable grid.
And furthermore, because they use naturally occurring, perfectly identical atoms, and they park those atoms in highly stable atomic clock states when they aren't actively being pulsed into the Rydberg state, their coherence times are absurdly long. We aren't measuring their coherence in fractions of a microsecond. We are measuring it in full seconds.
It is a profound paradigm-shifting capability in hardware. But while neutral atoms are scaling up by floating in a vacuum, another frontier is focusing on taking solid-state chips and pushing them to a level of extreme purity that borders on the obsessive.
Silicon spin qubits?
Yes, silicon spin qubits. Silicon quantum computing, or SQC, recently made waves by announcing an 11-qubit atom processor with a remarkable 660 millisecond coherence time.
That is nearly an eternity in the solid-state quantum world. But to get the kind of jaw-dropping coherence in a silicon chip, you have to achieve what the industry calls extreme purity.
Let's unpack exactly what this requires. Natural silicon, the exact material making up the classical chips in your laptop or phone right now, is actually a mix of different isotopes.
Right, about 4.7% of naturally occurring silicon is the isotope silicon-29. For building a classical computer, that 4.7% doesn't matter at all. The transistor doesn't care.
But for building a delicate quantum spin qubit, that silicon-29 is a disaster.
It is a disaster because silicon-29 has a nuclear magnetic spin. The nucleus acts like a tiny vibrating magnet to a delicately isolated electron spin qubit trying to maintain its superposition. That 4.7% of silicon-29 acts like a chaotic, fluctuating background magnetic noise storm.
The phase damping again.
Exactly. It is exactly the phase damping, the loss of rhythm we discussed earlier. The qubit gets constantly jostled by the magnetic fields of the surrounding silicon atoms.
So to fix this, scientists can't just cool the chip down. They have to change the actual atomic makeup of the material. They go through an incredibly arduous, astronomically expensive process to isotopically enrich the silicon.
They literally strip away and centrifuge out the silicon-29 atoms until they are left with a crystal lattice that is 99.9999% pure silicon-28.
And silicon-28 is magic for this application because it has zero nuclear spin. It creates a physical environment that is magnetically silent. When you place your electron qubits inside this perfectly silent, purified lattice, there are no vibrating magnets to bump into them. Their coherence times absolutely skyrocket.
It's like trying to listen to someone whisper an incredibly complex secret across a crowded, screaming football stadium and deciding that the most logical, effective solution is to literally physically remove 99.9999% of the screaming fans from the stadium until it is dead silent.
It's an unbelievable feat of material science. But if we're talking about unbelievable feats, if we are talking about moments that will be written in the history books, we absolutely have to discuss the Google Willow breakthrough from December 2024.
Yes, the Willow announcement was a watershed moment. It fundamentally shifted the timeline of the entire industry.
Google Willow is a 105-qubit superconducting processor. But what made this announcement historic was not just the raw number of qubits. It was the fact that they successfully, definitively demonstrated below-threshold quantum error correction using a topological surface code. Let's break down what that actually means because it cracked a 30-year theoretical challenge.
For decades, theoretical physicists predicted that if you could build physical qubits that were good enough, meaning their inherent error rate was pushed below a certain mathematical threshold, you could group many of them together into a single, highly stable logical qubit.
Okay.
The theory stated that once you cross that threshold, simply adding more physical qubits to the group would exponentially reduce the logical error rate.
It was a beautiful theory. But actually proving that in a physical lab was an absolute nightmare because historically every time you added more physical qubits to a chip, you added more wiring, more heat, more microscopic TLS defects, and more crosstalk. Adding qubits usually just added more noise, making the overall system vastly worse.
Exactly. It was a vicious cycle. But Willow finally proved the theory right in hardware. They ran a distance 7 surface code, a highly complex geometric arrangement of data and measure qubits, and they definitively showed that scaling up the number of physical qubits participating in the code truly drove the logical errors down exponentially. The more you added, the cleaner the data became.
It proved that large-scale, fault-tolerant quantum computing is not just a mathematical fantasy. It is an engineering reality.
And the raw performance metrics they released alongside this error correction proof are just mind-bending. I want the listener to really absorb these numbers. They ran the random circuit sampling, or RCS, benchmark.
Let's briefly explain RCS. Random circuit sampling essentially asks the quantum computer to run a chaotic, highly complex, pseudo-random sequence of quantum gate operations, and then predict the statistical distribution of the final outputs. Because the operations are highly entangled and complex, simulating this distribution becomes exponentially harder for a classical computer with every qubit you add.
The Willow chip, with its 105 qubits, completed this highly complex RCS benchmark in under 5 minutes.
5 minutes.
To put that in perspective, the Google team calculated that if you took the absolute fastest, most massively powerful classical supercomputer on Earth today, a machine the size of a warehouse drawing megawatts of power, it would take an estimated 10 septillion years to complete the exact same computational task.
10 septillion years. For you listening, 10 septillion is a 1 followed by 25 zeros. That amount of time is vastly, incomprehensibly longer than the entire age of the universe. It is a computation that outlives the cosmos, completed by a glowing chip in a cryogenic fridge in 5 minutes while the researchers drank a cup of coffee.
It is the most definitive, mathematically verifiable proof of beyond classical computation ever achieved. They also ran the quantum echoes algorithm, which measures out-of-time order correlators, essentially running time backward in a quantum simulation to measure chaos, and Willow performed it 13,000 times faster than a leading supercomputer. The sheer computational density is breathtaking.
Which forces us to ask a really profound logistical question. We talked about all the saboteurs on Earth. If earthly laboratories are endlessly plagued by cosmic rays from space, thermal vibrations from the ground, infrared radiation from the walls, and the physical weight of gravity pulling on neutral atoms, where is the absolute ideal place to actually put a quantum computer?
The literature points to an answer that sounds straight out of a novel: space.
Space, the ultimate quantum environment. Let's talk about why orbital space is so perfect for this. First and foremost, space gives you microgravity and a near-absolute zero cryogenic vacuum entirely for free.
Think back to those neutral atom traps we discussed, where lasers have to hold the rubidium atoms in place. Here on Earth, the unrelenting force of gravity is constantly pulling those massive atoms downward, and the optical tweezers have to constantly expend energy and tightly focus the light to fight that downward pull, which introduces noise and heating. But in the microgravity of low Earth orbit, neutral atoms simply don't fall.
They just float perfectly.
Yes. They can be manipulated in perfectly symmetric, highly relaxed optical traps for seconds or even minutes on end, without ever having to fight the Earth's gravity. The fidelity of the gates would theoretically skyrocket.
Furthermore, in the hard vacuum of space, you don't have the microphonic resonator shifts caused by acoustic vibrations. There is no sound, no seismic rumbles from passing trucks. The ambient electromagnetic environment, if you shield against solar radiation, can be radically quieter. It is a profound irony of physics. The harsher, colder, and more inhospitable an environment is for biological, warm-blooded human life, the more perfectly hospitable and welcoming it is for delicate quantum information.
It makes perfect sense from a thermodynamic perspective. We are loud, hot, chaotic biological systems. Quantum computers require silence, cold, and extreme order.
It really makes you wonder if the massive data centers of the future won't be built in Silicon Valley or Iceland, but will actually be orbiting the moon, beaming quantum data back to Earth via entangled photon lasers.
It's very possible.
And that massive scale of computation, that world-changing potential, brings us to the fourth and final part of our journey today: the implications.
We have spent the last hour discussing the how and the what. Now we must discuss the so what. What does all this incredibly dense physics mean for our ethics, our global economics, and our society?
Let's start with the most urgent, immediate implication, the one keeping intelligence agencies awake at night. The cybersecurity threat, often referred to in the defense community as Q-Day.
Q-Day is the hypothetical future date when a sufficiently large, fully error-corrected quantum computer successfully runs a specific mathematical protocol called Shor's algorithm. If a machine can run Shor's algorithm at scale, it will completely trivially break RSA 2048 and elliptic curve cryptography.
And just to ground that for the listener, RSA and elliptic curve aren't just obscure math. These are the foundational cryptographic protocols that currently secure essentially the entire global internet. Every bank transfer, every secure email, every software update, every classified state secret transmitted over a wire relies on the assumption that factoring massive prime numbers takes classical computers thousands of years.
A quantum computer using Shor's algorithm changes that timeline from thousands of years to a matter of hours or minutes. Experts currently estimate this would require a machine with a few thousand fully error-corrected logical qubits. We aren't there yet, but Google Willow proved the path is clear.
And because of that looming inevitable threat, we are seeing aggressive nation-states engaging in a highly concerning strategy right now today called Harvest Now, decrypt later.
This is a massive intelligence operation. Nation-states are currently using massive data centers to sweep up and store petabytes of heavily encrypted, highly classified data passing over global networks. They absolutely cannot read this data today. But they are hoarding it, knowing that in 10 or 15 years, when a massive quantum computer comes online, they will simply use it to instantly crack open decades of stored secrets.
The threat is retroactive. That reality is driving a massive panicked migration across global governments and banking sectors to adopt post-quantum cryptography, or PQC. These are entirely new mathematical encryption algorithms designed to be resistant to quantum attacks. We have to secure our networks today before Q-Day arrives tomorrow.
But the beauty of quantum mechanics is that the sword cuts both ways. While quantum computation threatens our classical encryption, quantum physics also provides the ultimate unbreakable defense through a technology called quantum random number generation, or QRNG.
I love this concept. Classical computers, by their very nature, cannot generate true randomness. They are deterministic machines. When your computer gives you a random number, it is actually using a highly complex pseudo-random algorithm based on a seed value, like the exact millisecond on the system clock. If an attacker knows the seed in the algorithm, they can theoretically predict the random number.
And if they predict the random number used to generate an encryption key, your security is broken. But a quantum system is fundamentally different. Measuring a qubit that is in a perfect state of superposition yields an inherently fundamentally random outcome. It is not an algorithm, it is a law of the universe dictated by quantum mechanics. You can use this physical uncertainty to create truly, perfectly unbreakable cryptographic keys.
So the technology breaks the old mathematical locks, but it allows us to forge perfectly unbreakable physical new ones. That is the security side. Beyond security, looking at the literature, there's an enormous economic windfall projected. Financial analysts are citing a conservative $250 billion value across various industries in the coming decades. And to really understand why it's worth that much, let's look at just one specific industry, pharmaceuticals.
The pharmaceutical industry is currently facing a massive scaling problem. Right now, bringing a single new effective drug to market can cost up to $4 billion, take well over 10 years of development, and it still faces a staggering 90% failure rate in human clinical trials.
Why is it so inefficient? Because right now, we largely use physical trial and error to see how complex chemical molecules interact with biological proteins. We physically mix things in wet labs and see what happens. And you might ask, why don't we just simulate the molecules on a supercomputer to see if the drug works before we make it?
We can't, because classical computers simply cannot simulate large, complex molecules accurately. The reason is that molecular bonds, the way electrons share energy and bind atoms together, are fundamentally inherently quantum mechanical in nature. The electrons are in superposition. They are entangled. Trying to simulate the exponential complexity of quantum electron interactions using classical ones and zeros quickly overwhelms even the largest supercomputers on Earth.
But a quantum computer doesn't have to translate quantum mechanics into classical math. It operates on those exact same quantum rules natively. It can theoretically simulate complex molecular interactions at the fundamental atomic level with perfect 100% fidelity. It effectively promises to replace years and billions of dollars of blind physical trial and error in a wet lab with perfect instant digital simulation.
The impact on human health, longevity, and disease eradication could be absolutely unprecedented. We could design bespoke molecules to bind to specific cancer proteins without side effects.
It is the ultimate promise of the technology. But as we reach the end of our vast stack of sources today, there's a deep philosophical implication that the literature, specifically the writings of analysts like Brian D. Colwell, asks us to seriously consider. And it goes all the way back to that isotopic purity we discussed earlier, spending vast amounts of money, time, and energy to strip away natural silicon to create 99.9999% pure silicon-28.
Colwell poses a truly fascinating, deeply critical question regarding this pursuit. He asks if we are currently experiencing a severe form of technological determinism. Think about it. Our elegant theoretical mathematical models of quantum computation require perfect, noiseless, isolated two-level systems to function.
But nature, the physical universe, doesn't actually provide perfect, isolated systems. Natural silicon is messy. It's a mix of isotopes. Atoms vibrate. Cosmic rays fly around. Heat exists. Nature is inherently inherently chaotic and interconnected.
Exactly. So rather than adapting our theoretical mathematical models to encompass and utilize natural, messy materials, we are stubbornly, forcibly reshaping matter at the atomic level simply to force reality to fit our pristine mathematical abstractions. We are demanding that the universe act like our chalkboards.
We are literally bending reality to fit our math. And when you look at the thermodynamics of this effort, it is equally wild to think about. The second law of thermodynamics, one of the most unbreakable laws in physics, dictates that global entropy, which is essentially disorder and chaos, always inevitably increases in the universe.
Yet, to build a quantum computer, we are trying to do the exact opposite. We are creating these tiny, microscopic pockets of extreme order on a silicon chip, perfectly isolated from the universe's natural noise. But physics demands a toll. The massive, room-sized, steam-proof cryogenic refrigeration systems required to suck the heat out and create that tiny pocket of cold order generate far, far more chaotic entropy and heat exhaust outside the system than they reduce inside it.
It's like we are running massive, blazing hot engines just to keep a single snowflake perfectly frozen. It leads to a truly thought-provoking question to end on. We are currently spending billions of dollars, and the brightest minds of a generation, violently fighting the fundamental quantum mechanical noise floor of reality itself. We are fighting the universe. And every single step forward, every extra qubit, gets exponentially harder to isolate. Is nature trying to tell us something?
It is a profound question. Perhaps we are on the wrong path by trying to suppress and isolate all material complexity. Maybe the true future of quantum computation isn't about perfectly isolating a chip from the universe, but rather finding entirely new paradigms where we learn to compute with the disorder, utilizing the natural chaos rather than endlessly fighting against it.
That is an incredibly powerful, humbling concept to leave you with today. As we move from these noisy, intermediate-scale quantum devices, these NISQ machines, into the rapidly approaching era of massive utility-scale quantum supercomputers, the hard lines between abstract physics, information theory, and physical reality are completely, irrevocably blurring. When we finally build a machine that perfectly, flawlessly isolates a tiny piece of the universe just to perform our human calculations, are we simply observing nature at its deepest level? Or are we fundamentally rewriting the rules of what physical matter can be engineered to do? That is something for you to deeply mull over the next time you look at the classical sequential smartphone or laptop sitting in front of you.
It truly fundamentally changes your perspective on the physical world.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us on Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.